company says that women managers in their company earn an average of $53,000 per year with a standard deviation of $5,000. Janice wants to test the claim. She surveys 25 women managers and obtains the following data on income per year. And here's the data right here. All right? Assume the population is normally distributed. What do you think Janice should conclude about the claim? So this is a hypothesis test. The company makes a claim about what they pay their women managers. We have sample data already gathered for us, and we want to test the claim the company made using the sample data we've gathered. Okay? So for hypothesis test, we start with step 1. State the hypothesis. Okay? In this case, what is the company claiming? The company claims that women managers in their company earn an average of $53,000. That's what they're claiming. That's the claim about the population parameter. In this case, the parameter is the population mean. So the hypothesis in this case is mu equals 53,000. Okay? That's our hypothesis. That's the claim we're testing. Step 2. Assuming the hypothesis is true, identify the sampling distribution. So since we are testing the mean of the population, the statistic that we care about from our sample data is the sample mean. That's going to tell us most about our population mean, right? Most of the time, the sample mean and the population mean should be close. That's what we expect. We want to know, based on how far our sample mean is from the population mean, how likely is that to happen? How likely is it that our sample mean is as far as it is away from our population mean? So we want to know about how sample means are distributed. Okay, so we want our sampling distribution to be the sampling distribution of sample means, which is given to us by the central limit theorem for sample means. According to the central limit theorem, sample means are normally distributed with a mean equal to the mean of the underlying population, and the standard error of the distribution equal to the standard deviation of the population divided by the square root of the sample size. Okay? So in this case, the mean of the population we assume is 53,000. Remember, we're testing this, but to construct our sampling distribution, this is what we assume to construct it. So 53,000. And we are told what the population standard deviation is. If we weren't told, this would be a more difficult problem. We'd have to use the t-distribution instead, right? But we are told. We are told that the standard deviation of the population is $5,000. So assuming that's true, we'll have 5,000 over the square root of the sample size. We surveyed 25 women, so that's our sample size. Okay? So that is our standard error, 5,000 over square root of 25. Let's throw that into a calculator, just so we get a feel for what that is. So our standard error is our population standard deviation, 5,000, divided by the square root of the sample size. We surveyed 25 women managers, so that's our sample size, 25. And we get 1,000. That's the standard error. So if we were to simplify this just a little more, then our sample means, our sampling distribution of sample means has a mean of 53,000 and a standard error of 1,000. Okay, step 2 done. Step 3, find the probability. For this step, the idea is we want to find the probability based on the sampling distribution, which is itself based on the assumption that the claim is true, that the population mean is in fact 53,000. We want to find the probability of obtaining a sample with a sample mean at least as unusual as the sample mean we actually found. Okay? Now to do that, we actually need to find the sample mean. We haven't done that yet, right? So let's take a moment and actually find the sample mean. So we're going to need our list of values, our data values. These data values right here, I have them off to the side so I can copy and paste them into my calculator. So I'm going to paste them right in here, combine them into a list, and I called the list X. Okay, let's just count them up, see how many I have. And I have 25 data points, which is good, right? My sample size, I am told, is 25. I interviewed 25 women managers, so I should have 25 salary ranges here, okay? And then to find the mean, to find X bar, I just add up all my sample data values and divide by how many there are. And so the sample mean is $50,283.36. That is the average salary of these women managers. Do notice that that is below the claimed population mean, right? The company claimed that the average was $53,000. Okay, we're saying that, well, from our sample, it looks to be a little bit lower. That doesn't necessarily mean the company's wrong, right? The company could still be right, and maybe we just got a sample with especially low salaries, okay? But we are going to complete this claim to see, or complete this hypothesis test to see how likely that is to actually have happened, okay? So because the actual population mean is claimed to be $53,000, if we kind of draw the sampling distribution here, something like this. So the actual population is claimed to be at $53,000. This is quite a bit lower, so it's over here in the lower tail. $50,283.36. So the probability we want to calculate is the probability that from a randomly selected sample, we would get a sample mean further from the claimed population mean as the sample mean we actually got. We want to calculate this probability here, probability corresponding to this area, because any data value over here is going to be further away from the population mean the company claims than the sample mean we actually got. So this would actually be a worse result, okay? So we want to look at the probability that we get a result like ours or something even worse, okay? That's what we're calculating. So we want to calculate the probability that a randomly chosen sample has a sample mean less than $50,283.36. Now, this is a normal distribution, so to be able to calculate this, we need to first calculate the z-score. Remember, the z-score is our particular value minus the mean of the distribution over the standard deviation or standard error of the distribution. Now, we have all these pieces. The x bar we have is $50,283.36. The mean, if we go back up to our sampling distribution, the mean is $53,000, and the standard error is $1,000. So 53,000 divided by the standard error, which is 1,000. Let's plug that into a calculator. So our Z is our sample mean, and I'm going to use my variables here so I don't have to write out those big long numbers and risk making a mistake, minus the population mean of 53,000. I don't have that stored in a variable, so I do have to write that out. And then divided by my standard error, which is $1,000. Okay? So I used variables where I could. If you want to just use the numbers as they are, that works too. You'll get the same answer. You'll get the same z-score of negative 2.71664. Okay, so this probability that we're trying to calculate based on the z-score is the same probability that z is less than negative 2.71664. So now that we've converted the probability, the probability formula to 1 over the normal distribution, the standard normal distribution, I should say, we are ready to calculate the probability using this p-norm function. So I want probability of a standard normal distribution. And my probability actually is in the lower tail, so I don't have to do anything fancy here. I just plug in my z-score. So I'll just put in z, or you could put in negative 2.71664. Okay? The probability I end up getting is 0.0032974415. Okay? So that's this probability here. 0.0032974415. Okay? So we calculated the probability. That's what step 3 was. Step 3 tends to be the longest step because of that. Okay? It could take a minute to calculate that probability. Finally, we're at step 4. Draw a conclusion. Now, the idea here is we've gone this whole way. We've done all these calculations assuming this is true. Okay? But what probability did we get? We got 0.0032974415. That's a very small probability. That's less than 1% chance. Okay? So if the original hypothesis was true, if the company's claim was true, then the chance that we get the kind of sample that we do, the kind of sample mean that we actually calculated, the chance that we get that kind of sample mean is less than a 1% chance of happening. Okay? So what do we conclude? So this is a judgment call, but in this case, the probability is so low that I think there's only one thing that we are likely to conclude. Since the probability of randomly choosing a sample is so small at 0.0032974415, that guy, that's less than a 1% chance of happening. Okay, assuming that hypothesis was true. We have two options here, right? We could either say, gee whiz, we're super lucky. We got this really unlikely thing happen. Or we could say, this is so unlikely, I don't think I could possibly be that lucky. I think the better explanation is that the claim, the hypothesis, is actually not true. Okay? And in this case, the probability is so small that we are going to conclude that the hypothesis is false. And so we conclude that what the company's saying, that the average amount that they pay their women managers is $53,000. We're saying, no, I don't think so. We talked to 25 women managers, and their average is so much lower than what you've claimed that we cannot accept that what you're saying is accurate. The chances of us doing this by accident are less than a 1% chance if what you were saying was true. And so instead we think that what you're saying is not true. The average is not $53,000.